All right. So what we want to do now is we want to talk a little bit more about energy and E-fields. But specifically, in this video, we're going to introduce this new idea called electric potential. Okay, and talk about why that's such a useful concept and how is electric potential different from electric potential energy, and talk a little bit more about units for that and all kinds of good stuff. So here we go. So what I want to do is I want to talk about this idea, electric potential, but to get there first, I'm going to refresh your memory on a little bit of older material. So you'll recall that when we were first talking about electric fields, right? We were talking about having, look, here is some great big charge. We'll say, look, great big charge plus Q. And would have said, I wanted to talk about how strong this guy's influence was, its electrical influence in the area around it. And we said, I'd like to be able to talk about this. And this is at the time we had just done Coulomb's law and the force between charges. And we said, we'd really like to be able to talk about at a particular location, like say right here, how strong is this guy's influence on electric charges here? Obviously, it's going to be stronger than over here, farther from it, that its influence should be weaker. Because we'd like to be able to calculate that. And so at the time, we said, imagine I put a little charge here. Look, here's a little positive charge, little plus Q guy. And you say, if I put him there, he'll get repelled by this charge. There'll be this electric force on him there. And you say, oh, good, this is something we know how to calculate. We could use Coulomb's law. Electric force is Coulomb's law constant times the charge of the first guy times the charge of the second guy divided by that distance between them squared, right? We could say, hey, where this guy is, maybe that is some distance out we'll call R. Okay. And we said, oh, good, we could calculate, we could plug this formula, we could find that force. Let's say we calculate it out, and it comes out to be 10 newtons of force. Can we say that this is a 10 Newton location then? And talk about this guy's influence that way? Well, sadly, the answer is no. Because what if I had put a charge here that was twice as big at that location? Well, then the force would be twice as big. It wouldn't be 10 Newtons, it'd be a 20 Newton location. You're like, I want to have a value that's just tied to this location. It doesn't matter what other little charge I put there. I just want to know how big this guy's influence is there. So what we have to do is basically take this charge out of the calculation, right? What we're going to do, what we did, you'll recall, I'm sorry, let me move on, is we divided out the Q on both sides. The little charge we're putting in out near this guy. When I do that, look, that Q drops out of the calculation, and I get what I wanted, an equation that talks about this guy's influence at this location. And I just have to plug in this constant, the size of this guy, and how far away from it I am. KQ over R squared. Now, what I'm talking about now is not the force at that location, the electric force, but the force per coulomb of charge that I put there. So for every coulomb I put there, that force will be this many newtons out. What we called this was electric field strength, capital E. And it was my force per coulomb at that location. And it's important that this is a value of that location in space. It doesn't make sense to say, how big of a field does this guy have? Or how big of a field does this guy have? What matters is at that location, how strong is the field that this guy's making? So that was that idea. We talked about the force per charge, and we've done tons with this idea since. A lot of last unit was dedicated to calculating electric field strength. Let me go ahead and draw that in here. So this guy is going to make an electric field that radiates outward, like so. All right, there's my E. All right, so what I want to do now, that was old news, now new stuff. I'd like to do something similar, but for energy. I'd like to talk about when I'm near this guy, and I go ahead and I put someone down here, like how much energy we'll have stored up, right? So you say, okay, well, that's fine. Look. We figured out these formulas for the last lesson. We figured that UE is KQQ over R. This is the energy stored up, and for these two charges being this far apart. You say, great. So if I want to know an energy for putting things at this location, this far away from this guy, could I just put a little charge Q there and do the calculation, boom, boom, KQQ over R, and that'd be my answer, right? And so you'd say, so then UE is KQQ over R. You say, is that what I'm after? You say, well, no, because what if I put a charge twice as big at that location? If I double that Q, it'll double the U. I want a value that I can like put a little sign in the ground there and say, hey, right here, this guy, the amount of energy I've stored up for this location is this much. And you're like, how am I going to do that? Well, just like we did before, we're just going to take that little q out of the calculation. Instead of talking about my potential energy, I'll talk about how much energy I would have stored up here per coulomb of charge that I put there. For every coulomb charge I put here, I'd have this much more energy stored up in the system. That's the way we're going to think about it. So I'm just going to divide out both sides by Q. So I'll divide out little q there, little q there. Bam, bam. And I get what I want. Look, I've got an expression now that'll depend just on the Coulomb's law constant, right? The size of this charge and how far away from this charge I am. At a certain distance away from this guy, some distance r away, there would be this much potential energy stored up in the system for every coulomb of charge I put here. I'll talk about my energy per charge, joules per coulomb, okay? That's this quantity. And this is, again, a quantity for a location in space. I can say this location has this value. We're going to give this its own symbol. The symbol that we use for this is a capital V. Okay? Now, I'm going to put some little serifs on it there. There we go. Capital V. All right? Now, what we call this, all right, and this is, be careful with this, this is called the electric potential. Now, wait a minute. What's the UE called? Electric potential energy. This is called electric potential. I know the names are really similar. This is a property of a location. This is something a system of charges has. This is a property of a location in space. I can put a little sign in the ground that says V is this big. All right? So that's this guy, electric potential. Now, it turns out that of all, you know that I've taken like lots of science courses in my years, right? And I've taken courses in all different areas of science, right? And over the years, I've seen, learned a whole lot of cool stuff. But out of every subject I've studied, the one that has the worst naming system of anything I've ever come across is this subject of energy and electric fields. So what I'm going to do is I'm going to make kind of a little chart to kind of tell all these different variables apart and what the symbols are for them and the names are for them and the units are for them. You can kind of help identify what the heck is going on in the problem, okay? And so as I do that, I am going to introduce a couple new equations as I do so. But let me go ahead and start making that chart. Now, I think you can see over to around here on the screen, I think. So I'm going to try to squeeze it into this area, this here, okay? So I'm going to make 3 columns, and I'm going to talk about the terms as we go. I'm going to start with some older vocabulary terms and work my way to the new ones. And so what I'm going to put the variable, the symbol that we use for it in formulas, and then the name, and then the units it's in. So here we go. So going way back to the start, you say, hey, what's this? Fe? You're like, that's the electric force. And that would be in units of newtons. What's this? That's the electric field strength. And that's in units of newtons per coulomb. All right, remember that's going to be my Fe per Q, right? Fe per force per charge at a location, right? The property of location. Newtons per coulomb. Now, by the way, there's going to be another unit for it that'll show up there. Okay, hang on, we'll come back to that. Okay, we then introduced this guy in the last lecture, UE. What's that? That's electric potential energy. And that would be in units of joules, right? Newton times a meter is a joule. Now, oftentimes when we're talking about moving electric charges around and stuff, I might just say, hey, what's the potential energy here? And you know by context, I mean the electric potential energy, right? So sometimes this will just get referred to as the potential energy. And we know by context that we mean electric potential energy. All right, what's this symbol? What's this variable? Delta UE? Like, oh, that's the change in energy. Okay, that's the change in electric potential energy. And then, of course, would also be in joules. Why does this matter? Why am I bothering to write delta UE? Remember, when we do energy calculations, the big formula we always use is sigma W is delta K plus delta U. You know what I'm saying? It's almost always, you say, the change in the potential energy that we care about. Because that'll tell us how much work we get out or how much kinetic energy we get out. The delta is usually important. And remember, with potential energy, you got to choose somewhere to call zero energy arrangement. You can almost always pick a spot to be zero. So you just, anyway, but getting back to this, I'm sorry. Let me just move along. So delta UE is worth talking about. And you'll see as we go on why it's even more important. Okay, so that, good enough. Now our new variable, big V. All right, capital V. This is called the electric potential. All right. And yes, that is very similar to the name electric potential energy. It just doesn't have the word energy on the end. So you got to be careful when people are talking about it. Wait, do you mean the V or the UE? Right? A lot of times we're talking about this, people will drop the word electric from the front, just talk about what's the potential. Now remember, this is a property of a location in space. So they'll be saying something like, hey, what's the potential here? Or what's the potential here? And you're like, oh, okay, at a location, I'm talking about V. All right? A lot of times, like I said, they'll drop the word electric and just call it the potential. Now the units for this, you say, look, our formula is that V is the UE per Q, right? So my units should be energy units over charge units. So it's going to be joules per coulomb. How much energy we have for every coulomb of charge I put here, I have this much potential energy stored up in that system. All right, that's big V. Now, joules per coulomb, it's fun to say, but it's a little long. And so they came with a new name, okay, a new unit just for electric potential. What they call it is volts. A joule per coulomb is equal to a volt. Now I want you to notice the problem here. What happens if I'm talking about my potential at a location? I say, hey you, tell me what the potential is here. And you say, oh, okay, my potential is 10 volts. You see the problem with having a variable that's V and a unit that's measured in V? You see what I'm saying? Is this like 10 times the voltage or is this 10 volt, you know? So here's the deal. What I do when I handwrite stuff, I try to make my symbols look different than my units abbreviations. So what I do is I put the little lines on top. They're called serifs, right? And I put them on top of the V for potential. So I can tell the V for potential apart from the V for volts. Okay, this is just something that I do. Did my high school physics teacher show me this? Maybe. This might be one I came up with on my own, I'm not sure. I do something similar, but actually backwards. When I talk about work and watts, right? You might remember that work is capital W, right? But when I go to do watts, the unit for power, I put serifs on that W to make it look different. Usually, no. And so I wish now in hindsight, I almost wish I'd done it the other way around so that it would like match up. Because right now with the W's, I'm not putting the serifs on the one that's the variable. I'm putting the serifs on the one that's the unit, right, for watts, right? But with this, I'm putting the serifs on the variable and no serifs on the unit. There's no consistency there. What can I say? Basically what I'm doing is the one that I use the least is the one I put the serifs on. I think was my original thinking on this. But anyway, I'm not sure if that's quite true here. But there you go. So that's the difference there. So I'm just saying you'll see that when I handwrite things, I put little serifs on top of the V's for electric potential to make it look different than before. Okay, moving on. It's going to get a little different now. You say, I got something else to add, and that is this V value, again, remember, it's a property for a location. So maybe I'm talking about this guy. Hey, look, it's right here at position A. I might talk about the potential at location A. And maybe I'm going to move this guy over here to position B. And I might talk about the potential at location B. Or I might be interested in just talking about, as I go from here to here, I might want to talk about the delta V. Okay, leave a little space here. I should have left a little more space. What is this delta V then? Like, oh, well, that's the change in electric potential is what you would say. How do you calculate a delta? Well, you always take the final minus the initial, right? That's how you do a delta, final minus initial. And so in this case, going from A to B, this would be the V at B minus the V at A, right? That's the way you calculate it. So because we calculate, we're always doing a subtraction. We're taking the difference between the two values. The most common name for this delta V guy, we call it the electric potential difference. That's the name for this. The electric potential difference. Now, a lot of times, people will leave the word electric off, and they'll just call it the potential difference. And we know it's delta V. At which point, you're starting to think, yeah, those names, they really are getting kind of similar. Electric potential energy, electric potential difference. Or potential energy, potential difference. You're like, it's starting to get a little, we got to be a little careful. What would the units be on delta V, by the way? I'm going to take something in volts minus something in volts. It'll be in volts, right? Again, it'll be in joules per coulomb or volts. But this is where it gets even a little nastier. You know how V is measured in units of volts? Sometimes then, people just call it the voltage. And they'll say, hey, what's the voltage at this location? So this is also called voltage. But you know when you calculate a delta V, right? Electric potential difference, final minus initial, that'll also be in volts. And so people will also sometimes call this voltage. You're like, what? I guess I can see how that could happen. So the point is, you have to know by context, are they talking about the difference between two spots or right at one spot? Annoying, huh? But we're not done, all right? There's even more. Wait, there's more. This variable here that we're talking about, this thing, this potential difference, delta V, in the old days, all right? We didn't have computers with like word processing. You couldn't do a whole lot of different fonts. In fact, if you wanted a fancy font, like say italics, like some typewriters would have extra keys that can do italics, right? My family had one like that actually at one point. But anyway, the point is, you certainly didn't have a typewriter that could type deltas. So if you needed to type delta V, here's how they used to get around that, not having a delta key. What they would do to do this calculation, they would type in the typewriter V, and then they would roll the paper up a half a line, and then they would type BA as a subscript. And so anyone that read that would know, oh, when I see two subscripts after it, I know that's a potential difference. That's VB minus the V at A. This means this, okay? That's the way they would type it. Basically, it's just saying, look, when I go from here to here, how much am I going up by or how much am I going down by in potential? You see that difference, that change in it, it's how much higher is the V at B than at A. It's the V at B with respect to A, or compared to A. How much higher is the potential or lower is the potential? Okay, that's what that means. Why is this important? Why do I bring this up? In the old days, they didn't have delta gates. We have them now. But here's the thing. Because this is what they used to type. When they wrote formulas, if the formula had a delta V, they would just type a V. And people had to know and remember, oh, it's really a delta V in this formula. For example, in next unit, like one of the most important formulas in circuits is called Ohm's law. And the formula is delta V is I times R. But in the old days, they wouldn't type delta, they didn't have deltas, so they just wrote it like this. And you just had to know, oh wait, when I see that formula, that's really a delta V. I will always write it as delta V is IR. Well, except for what I just did. I always write that. But just realize it's yet another irritating, weird thing about this subject. And it's a historical thing about not having delta keys on typewriters. But there you have it. So something else to know is sometimes in formulas, and I'll make a big deal out of it whenever it happens in a formula, they'll write a V when it's really a delta V. But wait, we're not done yet. There is something else annoying here. Watch this. Check this out. Do you see this symbol? Okay, that's kind of a curly, fancy, it's a script E. Okay, is what it's capital script E. Now, you've seen a symbol like this before. We use this symbol for the electrical permittivity, right? You remember in Coulomb's law, that constant, we use this epsilon naught, 8.85 times 10 to the negative 12, Coulomb squared per Newton meter squared, right? That was that electrical permittivity. We wrote that as kind of a little one. Oftentimes I'll write it like this as a lowercase epsilon. That's the way I like to write it, but sometimes you'll see it printed this way because they think you're less likely to get it confused with a lowercase e that way. Anyway, it doesn't matter. Point is, this is a big capital one. What is this? This is effectively, for most purposes, it's the same thing as delta V. It's the electric potential difference. But it's another symbol that they sometimes use for it. When they use this symbol, they'll oftentimes refer to it as the electromotive force, or the EMF, which is a terrible name because it's not a force, right? It's energy per Coulomb, energy per charge. It's not force. What a terrible name. A college professor told me that he thought that it was like a mistranslation, maybe going from one language to another, of the word for power and energy with the word for force. But the point is, oh my gosh. So this EMF symbol is effectively the same thing as delta V. You'll see this pop up when we start working with batteries. They'll oftentimes use this symbol to mean the delta V from one side to the other side of the battery. Or sometimes they'll use this, or we'll use this symbol at the very end of the course when we talk about energy and magnetic fields generating voltages. And we'll use this symbol for those voltages we generate. So there you go. And of course, it's the same thing as this. It's effectively the same thing as this, the involts. There. So what I'm getting at here is, look, we got a bunch of different terms. The names are really similar. Sometimes the notation's a little goofy, all right? And so you just got to be careful. When you read the questions, you got to read really carefully about what information they're giving you and what they're asking for you to solve. And you got to figure out from context, from like what units it's in, right? And be just real careful, all right? And that's something else that makes, can make it a little tricky. The other thing I want to point out here, I got one more thing to say in this video, and then we'll wrap it up and we'll call it done. One more thing, and that is that I'd like to talk to you about why are we doing this energy per charge thing? What's the point of this? Why are we, this whole unit is called a potential and capacitance, right? That's what this unit's about. Why is potential so important? Why is it so cool? Why do we do this business? Why don't we just do stuff with energy like always? Here's why, all right? Because you'll recall that there is no good way of directly measuring energy, is there? There's no tool that just, oh, stick it in, oh, I've got this many joules of energy. There is nothing that does that. There's no direct measurement of it. In fact, going back a step, there's no direct measurement of E field strength either, right? Not even E field meters. How do we figure this stuff out? It turns out there is a device that measures delta V. And it's really easy to use. Here, the device looks like this, okay? This one actually measures a bunch of different things. One of them is voltage. It's called a device that measures the delta V. It's called a voltmeter. This one's called a multimeter. There's a bunch of different things it can measure. I take my little probes here, right? Okay, and each of these guys, right? It's like a little cord, and it's got a little metal tip here, right? The probe. And I plug them in. The black probe always goes in the common socket, right? The red one goes in different places depending on what I'm measuring, current or voltage. I'm gonna measure voltage. I'm gonna turn my little dial to the right setting. I will talk to you more about this in detail when we do a lab with this. But I turn it like that. And now I have my two probes. Say I wanna know the delta V between A and B, between this location, all I do now is I just go and I touch it to the two locations, bing, bing, and it reads off my delta V. That's it, the end. You're like, oh my gosh, that's so nice. You can easily get a delta V. And once you have a delta V, if you know the charge that you're moving, how do you get a delta V? I took the V there minus V there. You know what that is? If V is UE per Q, then delta V is just going to be the delta UE per Q. So if I know the delta V, real easy to measure with a voltmeter, bing, bing, right? So this is really practical and useful. You just go bing, bing, multiply that, bring the Q over, multiply the charge, now you have the energy change. If you know the charge you're pushing an electron. Oh, it'd be electron charged by delta V. That's the energy change from moving from there to there. Isn't that cool? And so delta V, electric potential difference, I should say, the electric potential difference is really useful. An easy thing to measure and get values and analyze circuits and different situations. So that's why we're going to spend so much time here on delta V measurements and calculations, because it's something you can actually practically do, okay? And so last comment I want to make, we're going to do a bunch of calculations with like charges moving in electric fields and getting pushed around. And you could go and try to do the, oh my God, but it's a whole lot easier if you just measure your delta V, bing, bing, right? And then you say, look, I'm going to use my formula here. Delta V is a delta UE per Q. What will I do now? Check this out. Move the Q I'm moving over here. Q times delta V. That's the delta UE. And so what I'm going to do, when I go to do my big energy formula, where it says delta UE, I'll just do the substitution. Q times the potential difference. Q times delta V is what I'll substitute. And there's a super useful substitution that lets you do calculations a lot quicker. All right? Just plug that Q delta V in for the delta UE. All right. So that's it. That's the deal with that. This is now enough information for you to actually go and start cranking out some problems, okay? And figuring out how fast these particles are moving, right? You say, if I got an electron, it's like a known mass and a known charge. I can look them up on the table, or a proton, known values, and I can put them in here. I can find kinetic energies, find out how fast it's going, right? I can find out what the delta V is if I know that how much the speed has changed by, because I know the 1/2 mv squared, and I got the charge, because I know the charge is an elementary charge. Oh, that reminds me. I got one more term I got to share with you. Sorry. One more, last little thing, okay? Last thing. There's another unit for energy that I need to share with you real quick, okay? Okay, I'm gonna squeeze this in over here, okay? Two things. One, I'm gonna refresh your memory on this. Do you remember that there is a unit for charge symbolized like this? Remember what this is called? That's an elementary charge. It's the charge of one proton, okay? You might remember that 1e, okay, is 1.602 times 10 to the negative 19 coulombs, okay? That's the charge on a proton. Hey, what's the charge on an electron? It would be negative 1e. would be negative 1.6 × 10⁻19 coulombs, would be the charge on an electron. Okay, so that's called an elementary charge because they used to think that was the smallest, most basic building block of charge. Now we know that quarks have fractional charges. But anyway, that's the idea. Okay, next. So I want to introduce you to another unit. It's called the electron volt. Okay? So I want to talk to you about the electron volt. The symbol for it is lowercase e, capital V. That's the unit symbol. Okay? It's called an electron volt. Specifically, what it is, it's the energy change you would get if you sent a charge of 1 elementary charge, an electron, through a delta V of 1 volt. All right? That's what it is. So it's a useful unit if you're talking about things on the atomic scale and you're pushing just one little charged particle around, right? Electron volt. It's the energy change, so it's the amount of energy that you would get for accelerating an electron through 1 volt of delta V. Or for 1 elementary charge going through 1 volt of delta V. For an electron moving through 1 volt of delta V. Okay, so how big is an EV in joules of energy? Well, that's easy. I'll just take the charge, 1.602 times 10 to the negative 19 coulombs, times the delta V of 1 volt. And you say, it's for an electron going down 1 volt, negative, negative, makes positive. And that would be 1.602 times 10 to the negative 19 joules of energy. That's what an electron volt is. Okay, you'll see that on some homework problems. It makes it a lot easier if I'm doing problems where I'm moving, like I'm going to move a proton from, through 6 volts of potential difference. You're like, oh, that'll be 6 electron volts of energy I'll get out, right? That'll be a change in potential energy. Or what if I was going to move a calcium 2+ ion, right, through 10 volts of potential difference? You're like, oh, there'll be a change in energy of electric potential energy of 2 times 10, 20 electron volts. So that's it. That's that unit, electron volts. Okay, that's it. That's it. That's the last thing I want to say. That's a fair amount of vocabulary, yeah? And it's, like I said, it's a little bit, the names are kind of similar to each other. We're not expecting you to know it like right off the bat. Say, oh, obviously, it's it takes a little bit of time working with it. And as you work through the problem sets, right, you kind of pay attention to what quantities they're giving you and figure it out. Having a nice cheat sheet like this to start you off might not be a bad thing, which is why we did it. But yeah, that's it. Like I said, this is what you need to know to start doing some good energy calculations with charged particles. All right, I'll see you next time.